Hi, everyone. It's me, Carolyn, and we are going to be continuing in chapter 6 with looking at one particular discrete probability distribution. And this one has a variety of different uses and where it can be seen. Makes things a little easier when we have an experiment that we do over and over and over again. Say in the first section, we would list our possible values for X. Here, we're going to have a lot more values for X. And a lot of times we aren't interested in knowing all of them. We just are looking at specific situations. So I'm going to start by sharing my screen so that we can kind of walk through the guided notes. I will also be showing us in this video how we can use Excel and or StatCrunch to do some of the calculations for us. I will also do them by hand. So again, feel free to use whichever way you want to do it more comfortably. You can do it a lot of times by hand. However, some situations it may be a lot easier to do it using Excel, or in my class, we can use StatCrunch because you do have access to that. This is not something that you would probably do in your future unless you were going into statistics. So it's just, again, we're trying to give you a feel for some of the things that show up in a statistical world, some of the applications that are out there. And if you're reading on things, you'll be like, oh yeah, I remember hearing about that. So just kind of keep that in mind. We're not trying to make you experts in all of these things, just giving you a taste of all the different areas of probability and statistics. Okay, we are still talking about a discrete situation. And we're going to start off, and let's consider flipping a coin 40 times, and we're going to let X be the number of heads. What would this probability distribution look like? Well, we did it in 6.1. We flipped it twice. And X took on the values 0, 1, and 2. We drew our sample space and got our probabilities from there. So if you imagine trying to do that for this problem, well, X is going to take on the number of heads. Well, that could be 0, 1, 2, 3, all the way up to 40. And if I were trying to list all of the outcomes for this situation, I would have a very, very long list because I'd have 40 H's in a row. I'd have 40 T's in a row. I'd have a number of possibilities with only one H. I'd have two H's all over the place. So it would be mind-boggling and would take me a long time to do that. Luckily for us, we don't have to do that in this situation or situations like this, because this is going to be an example of a binomial. So first of all, the binomial has some properties for it to be considered a binomial. And as I go through these properties, we'll kind of check to see if this flipping a coin 40 times satisfies the situation. And this has been a distribution that has been studied over and over and over again. Hence, we don't have to do all the work. The work has been done for us. We can use the results from that. So the properties of a binomial, first of all, is the experiment is performed a fixed number of times. And each time is considered to be a trial. Okay, we are flipping our coin 40 times. So that's our fixed number, the number 40. So we are doing this thing 40 times. The trials are independent. Again, reminding ourselves that independent means that what happens on one flip doesn't affect what happens on the other flips. And if this coin is fair and we're using, it should be independent of each other. The trial has two outcomes or can be reduced to two outcomes. And we will consider these outcomes to be a success or a failure. And that's why this one is so powerful. This binomial is powerful, not because of the two outcomes, because in a head or a tail, but we can reduce it to two outcomes. So a success or a failure. And we'll see that happen over and over and over again. And the fourth one is that the probability of a success remains the same for each trial. So in other words, when I flip that coin, the 15th time, getting ahead is the same probability as when I did it the 30th time. that probability does not change from time to time. Okay, those are the 4 different properties that have to be satisfied in order to be a binomial experiment or a binomial distribution. And so let's look at the ones that we had. So the first, some other ones too. So flipping a coin 40 times and counting the number of heads. Is this a binomial? So did we do it a fixed number of times? Yes, we did it 40 times. Are the trials independent? Yes. One flip does not affect what happens on the second flip. Is there 2 outcomes, or can we reduce it down to 2 outcomes? Yes. We either get a head or we get a tail. Head is going to be considered our success. The probability remains the same for each of those. Yes, the probability is 1/2 every single time. Let's look at a few other ones and determine, are these or are these not binomials? So this one was a yes. Shooting a free throw 7 times. Is the number of trials fixed? Yes, we're shooting it 7 times. Are the trials independent? This is where we could probably argue that independence, if you make it the first time, it's going to affect how you shoot the second time, and so on. But then if you are a decent player, what happens the first time should not affect the second or the third or the fourth time. So that, I would say, yes, they're going to be independent. In our class, something like this will be independent. We will not start to get psychological in these problems. We kind of take all that psychology out. There are only 2 outcomes? Yes, either you're going to make it or you're not going to make it. Does the probability remain the same? That we will also say yes, because as you become a better ball player, that probability is going to be pretty consistent. Okay, so this one is also a yes. Okay, so let's draw a card from a deck 4 times with replacement and count how many hearts we got. Okay, so we're going to put the card back in the deck. Are we doing it a fixed number of times? Yes. We're drawing 4 cards. Are the trials independent? Yes, because we put the card back in. Okay, I'll put down here without replacement. If we didn't put it back in, what happens the first time will affect what happens the second time. So this without replacement, that's going to be a definite no, and it fails on number 2 and number 4. Okay. Trial has 2 outcomes, or reduced to 2 outcomes. Here we reduced it because all we're concerned about is if we have a heart or not. Our success is our heart. Everything else is considered a failure. So that would also be okay. And if we put the card back in the deck, that probability does remain the same. So if we do put it back in, this is a yes. If we don't, then it's a no. Okay. The next one, let's see if we roll a die until we get a 6. Okay, so the first thing is, do we complete this a fixed number of times? No, because it might take us 7 times to get this one. So this one fails in step. The very first thing fails. Roll a die 10 times, count how many 6s. We're doing it a fixed number of times. Trials are independent. What happens on the first roll does not affect what happens on the second roll. Outcomes reduced to 2. If we are only concerned if we get a 6 or not, yes. If we started looking at what number was on the die, then the answer would be no. But we're just looking at if it's a 6 or not. And the probability of getting a 6 is always provided we continue to use the same die, that 1 out of 6. So this one would also be a yes. Okay, so there's 4 things we kind of have to think through to see if it is a binomial. And then once it's a binomial, we have some nice things that happen. We can find probabilities based on these binomials. So in other words, if I were doing the chart for my probability on rolling this thing 40 times, I could use this formula to help me calculate all of those pieces instead of trying to recreate the sample space and hoping I don't miss one or two cases. Okay, first of all, we need some notation though. So we do need an N. N is going to be those fixed number of trials, like how many times you're flipping the coin, how many times you're rolling the dice, how many times you're shooting a basket. P is going to be that probability of a success, which remains consistent from each trial. So if you're flipping a coin, 1/2, rolling a die and seeing if it's a 6, 1 out of 6. Other textbooks, if you ever look in other readings, sometimes they will also introduce the idea of a probability of a failure in here as well, and they'll call that Q. So, but Q, if you have either a success or a failure, the probability of Q happening is simply 1 minus your P. So our text just uses 1 minus P instead. So you may see this P is listed in other textbooks as a Q. And then we're going to use a little x, which is going to be the number of successes that we're interested in the problem. Okay, based on what the question is asking us. Now, to calculate this probability, and we will go through this a couple of times by hand, and then I will also show you how to use technology to do so, to kind of help us save some time. So again, probability that our random variable is equal to some value is equal to this n, where n is the number of trials we have, factorial. If you remember, we did factorials when we did chapter 5. N minus x factorial, and then x factorial. Then we're going to multiply that by p, which is our probability of success, raised to the x power, and then 1 minus p to the n minus x. Some of you may recognize this first fraction as our combination piece that we had. So we can use an even faster method, is just use that NCX. And I will do both once, but I will probably most of the time just use that NCX button on my calculator to save me some time. And then P to the X and 1 minus P to the N minus X. And this is all multiplication going on in here. I did put the star right here because it's kind of hard to tell if I just put them next to each other. If something's being raised to a power or something like that. So let's do an example. And I kind of simplified my 40 times down to 8. And we're going to flip a coin 8 times. Okay. And we want to know what is the probability of getting 6 heads. So I like to, when I do these problems, I like to put my pieces down so I can kind of remember what's going on. So my N, that's the number of trials that we're doing. We are flipping this coin 8 times, so N will be 8. My P, that's the probability of a success. Since we are flipping a coin, that's the probability of getting a head, which is 1/2. And the X that I'm interested in is this 6. So I want to know what is the probability that X is equal to 6. Okay, so I'm going to put all my pieces in, then we will calculate it by hand. I will do another example, calculate it by hand, and then I'll go to my technology to show you how to do both of those using technology as well. Okay, so according to my formula, I need to do 8 factorial divided by 8 minus 6 factorial times 6 factorial. Then I'm going to multiply that by 1/2 or 0.5 if you prefer to the 6th power, and then 1 minus 1/2 to the 8 minus 6. I'm going to kind of clean this up a little bit before I go to the calculator, basically do some of the subtraction. 8 factorial. Here I have a 2 factorial times 6 factorial. Then I'll have my 1/2 to the 6, and 1 minus 1/2 is 1/2 to the 2nd. Okay. And I will show you my steps. If I'm going to do this all in one line, I need to be a little bit careful because I need to make sure that these two guys stay in the bottom. Hence the reason I do like to use that NCX a little and NCX more often, which I'll do in this second piece just to kind of save me some time. But if I'm going to do it this way, I usually do it in a couple of steps. I will take that 8 factorial, again, to find my factorial key. So there's my 8. I have to go to this PRB, and I have to go all the way over to my factorial button. I get that. I'm going to divide it by, and I'm going to put in parentheses, my 2 factorial times 6 factorial. And I like to get this number just because it's always going to be a nice whole number. So I get the number 28. And then I'm going to multiply that by, and I'm going to do 1/2. And I'm going to use the fraction, so 1/2. And I'm putting it in parentheses. And I'm raising it to, that's my little caret key here, raising it to the 6th power. Some of you have calculators that actually put things up in an exponent. If that's the case, when you come back down, make sure you do come back down to take that 1/2 and raising it to the 2nd power. And I'm going to hit equal to. This gives me a fraction, which is fine. I could turn it into a decimal, which might be a little nicer to look at. 0.109375. If I'm looking at the decimal form. If I had worked with decimals here and used 0.5 instead of the 1/2, I would have gotten that decimal to begin with. Okay. So I'm going to do this one again as well. We will use the calculator as well. And then I'm going to, like I said, I'm going to go to technology to kind of show us how we can do this using technology as well. So here we're going to do, what is the probability of getting 4 heads? And so instead of 6, we're going to do 4. Same pieces here. My N is 8. P is 1/2. This time X is 4. My little x is 4. And this time I'm going to actually use that combination notation. So that's telling me it's going to be N4. So my 8C4, and then multiplied by my 1/2 to the 4th, and 1 minus 1/2, 8 minus 4. Okay. If you had done it this way, we would have had 8 over 8 minus 4, and then 4 factorial here. Then you would add a 4 factorial and a 4 factorial as well. But the reason I like this is I have to get my factorial key in the same place. And when I do so there's my 8, I go right past that combination button. So I might as well just grab that one. Oops, I went too far. And then I type in the 4, and it does that whole fraction for me. So this whole fraction here is 70. And then I'll multiply it by my 1/2 to the 4th and my 1/2 to the 4th. If you have issues on calculating some of these things with your calculator, please come and get help. Either talk to me or email me or go find some other support from our math center. We do have a wonderful staff over there that can help you. I'm going to do this one using decimals, so we can see that it does give me just the decimal form. So there's my 70 in there. So I'm going to multiply that by 0.5, because that's 1/2, raised to the 4th, and then multiply that again by 0.5 raised to the 4th. So there's my keys in there. Hit my equal button, and I get 0.2734375. And again, make sure when you're entering these answers into your homework system, you do round it to however many decimals they want you to. Okay. I am going to show you now, again, I'm going to go to, think I'll go into Excel first. So let's go into Excel. And we will do these two exact problems again using Excel. And in the future examples that I have, I'm only going to use one or the other. I'll set it up on the basic screen, but I will then go to Excel or StatCrunch, and I'll mix it up so we see a little bit of both. But here, what we're going to do, if you're in Excel, the key is we're going to, again, use this functions. So that's my little FX key up here on the screen here. Hopefully you can see my piece. And we're going to look at our statistical category. And this is a binomial. So we're going to be looking for binomial distributions right there, binom.dist. We're going to grab this one, and I'm going to hit OK. Okay. Now, this one is set up a little bit different, so you kind of have to think about what they're asking. So this numbers that they have right here, notice they do give you a description, is the number of successes in the trials. So for our first one, our number of successes was the 6. The next piece is the number of independent trials. That's our N. And then we want our probability. The nice thing about Excel is that we can enter these fractions in here. So we would put 1/2 in there. And you'll notice it did do its conversions for us. Here, this cumulative, we'll talk about that in a different example. If we are adding a bunch of things, like we've talked about how to accumulate, like in the ogive, that means to add up. We aren't really adding up anything. We're doing it for a single value. So we're going to type in the word false. Okay. And you'll see that we did get that 0.109375. So there's my 0.109375. Okay, which is what we had when we did it by hand. I'm going to do the same again, just so you can see the steps for x equal to 4. So again, into our function, make sure you're in the statistical category, down to binomial distribution, binom.dist, kind of also tells you binomial distribution probability. So we're going to hit OK. Our numbers this time is 4. That's how many successes we wanted. The number of trials was 8. Probability of a success, that's our 1/2, probability of getting ahead. And our cumulative is false because we aren't adding up a bunch of pieces. So 0.2734375. Kind of makes me feel good when I check these using Excel, because it's like, okay, I didn't hit wrong keys on my calculator. All right, so this is how we can use Excel to find our binomial distribution. I'm going to now move to StatCrunch, so bear with me while we switch to StatCrunch. Okay, and here's my StatCrunch screen. And I don't need to type anything in, which is kind of nice because I'm just going to use some of the functions. And the functions that we're using, it's going to be under our stat. It is a calculation, so it's kind of under these calculator buttons. We have lots of different pieces here. You'll notice one is labeled binomial. Okay, so I'm going to click on this for us, and I'm going to pull this over. Hopefully this pop-up screen showed up for you. And this is the default, or it's probably showing you exactly what I had before. So the first thing we need to do is we type in the number n. So our number n is 8. My p is, the one thing we can't do, well, I guess we can. I'm going to put in my 1/2, and we want to know that x is, and it does have a drop-down menu. Here we're going to have equals and 6. And then I'm going to hit my compute. The nice thing here is that I like about StatCrunch, it does show us the picture. So you can kind of see the graph. Here's my 0, 1, 2, 3, 4, 5, 6, 7, 8. So it did all the calculations of that complete probability distribution. You'll see it is nice and symmetric. It's kind of bell-shaped. And right now it's giving you the height of this column by showing it to you in red. So there's that point 109375. The other nice thing I like about this is if we're doing multiple questions on the same problem, we don't have to type it in again. We can simply go in here and say, okay, now I need to do this for x equal to 4. I just went in, typed a change, and I hit my compute. Notice it got a different line and 0.273435. I really like StatCrunch with calculating binomials. It makes things a lot easier than even Excel, because Excel does have some quirks to it, and we'll see that a little later in some of our other examples. I am going to go back to our guided notes so that we can continue looking at some different examples. Again, I will set them up in the formulas on the paper, but I'm not actually going to plug through them. So I will set them up. So you'll see this piece kind of in here. I'll simplify it a little bit, but I'm not actually going to do the grunt work on the calculator. I will go to Excel and StatCrunch. I'll kind of do those two when we calculate them. So let's just do a couple more so we understand some of the other questions. Okay, so we're going to roll a die this time, and we're going to roll it 12 times, and we're going to let x be the number of times a 4 is rolled. Okay, and this time I want to know what is the probability that we see a 4 3 times. So let's get our pieces. So we have our n, which is our total number of trials. How many times we're rolling this die? It is 12. The probability of rolling a 4, that probability of a success, that is 1 out of 6. And then in this problem, what is the probability that we see a 4 3 times? So that's how many successes we have. So x is equal to 3. So according to our formula, it's going to be 12 factorial, and I'll set it up both ways. 12 minus 3 factorial, 3 factorial. And then we'll have that 1/6 to the third, and 1 minus 1/6 to the 12 minus 3. Okay, cleaning this up a little bit. 12 factorial. 12 minus 3 is 9. We'd have that 1/6 to the third, and 1 minus 1/6 is 5/6. We'd have that to the 9th power. And you would either calculate it this way on your calculator, or this would be our 12C3. To the 9th. Okay. Like I said, I'm going to set these up first, and then we'll go to our technologies to solve the 3 pieces that we have here. Okay, here we have, what is the probability that a 4 is rolled fewer than 2 times? So again, my n is still 12, p is 1/6, because our experiment has not changed. We're just changing our x. Now our x is going to be how many times we see that success. So fewer than 2 means, well, fewer is less than, strictly less than. So 0, remembering we could have a 0 or 1. So 0 or 1. What we need to do is actually calculate them twice and add them together. So we have to actually calculate the probability x is equal to 0 and add it to the probability that x is equal to 1. We did something like this given a table. So these probabilities that we're calculating are specific probabilities underneath those probability distributions. And if we want to find more than one, we have to add up the different pieces. Okay, and now we would simply put those pieces into our formulas and calculate. Okay, I've showed you how to do a couple of those. I'm going to just leave them here because now we need to calculate this one and we need to calculate that one and add them together. However, in Excel and StatCrunch, we have some extra pieces. Also want to remind us this is the same as x is strictly less than 2, or since we only have 0 and 1, we could think of it as being less than or equal to 1. Those are going to come into play when we look at Excel and StatCrunch. So I'm going to kind of keep those in mind. What is the probability that we see a 4 at most 3 times? So at most means, again, n is 12, p is 1/6, and x is at most, that means 3 or less. 3 or less. So that means 0, 1, 2, or 3. We could calculate all 4 of those. And if we were doing this by hand, this is exactly what we would have to do, because there is no shortcut. Hence why I like to use technology. You could calculate each one of those and add them together. Or we are trying to find the probability that x is 3 or less than or equal to 3. Okay, here was strictly less than 2, which was less than or equal to 1. All right, I am going to go into Excel first, and we'll work through these. So into Excel. I have a fly buzzing here, sorry. Okay, so I'm going to do that first one, x is equal to 3. So hopefully you still have your guided notes with those things written in there as you're watching me do this. So I'm going to go into, again, statistical category, binomial distribution, hit the OK. The number is the number that I'm asking about. So in that first one, it was 3, just plain old x equals 3. My trials was 12. My probability of a success was 1 out of 6. Notice it does turn it to a decimal for me. I like to leave it in fraction form. And cumulative, we're not adding anything, so this first one is still false. And I'm going to hit OK. I'm going to write those numbers down so when I come back to my guided notes, you will see that we do have those values. So there is when it was just x equals 3. Okay. This next one, we wanted the probability that fewer than 2 times. So fewer than 2. So again, we're going into binomial distribution. The number of trials, I'm putting the ones that haven't changed. Okay, and we wanted fewer than 2. This is where we want to make sure to do that strictly less than, because we're adding. We're starting at 0 and we're adding up to 1. So I'm going to do the 0 and 1. And here, I'm going to put in the word true. By putting in the word true, it is taking the probability of 0 and adding the probability at 1. So it's starting at the bottom end and going up. Excel does not allow us to start at some point and go from it up, only from the bottom to a certain value. So I'm going to hit the word true there. And I'm going to put that value down here as well on my paper. So 0.381333. We're going to do one more because we want the probability that x is less than or equal to 3. So again, function, binomial distribution, hit OK. Again, my this time we're going from 3, 0, all the way up to 3. And so I'm adding those bottom 4 pieces up, 0, 1, 2, and 3, adding them up, hence the true, hit my equal. I get 0.87482. Okay, so that's kind of how we can use Excel to help us. I will now take us over to StatCrunch. And we start all over here, just so you can remember. We go under Stats, Calculators, Binomial. Bring this over a little bit here. My N was the number of trials. We had 12. We were flipping that die or rolling that die 12 times. My P, probability of a success, is 1/6. That was the probability of getting a 4. And in the first one, we just wanted equal to. You'll see when I pulled this menu down that I was able to choose options. And that's why I kind of like StatCrunch for this, because a couple of things is it does draw the pictures for us. And here we just wanted x equals 3. So it does show the pictures. And you'll notice that kind of looks, remembering that we could have a 0 all the way up to 12. But our probabilities getting past here get very, very, very tiny. So you'll notice it is almost bell-shaped, but it is a little bit skewed to the right. For x equaling 3, that was at 0.197. And here we did have a few more digits than I did in Excel. Excel can show more digits simply by just adjusting the column size. Okay, so there it is for x equaling 3. If I wanted x to be, and here the nice thing I like is we can do strictly less than. So here is strictly less than 2. Notice it just highlighted the 0 and the 1. So you can see that it is strictly less than 2, so fewer than 2. And that gives me that 0.381. I can also change this to less than or equal to and put the 1 in there. And it's the same thing. So StatCrunch allows us to use strictly inequalities and less than or equal to inequalities. Also lets me go up the upper end, which we didn't do in this example, but I do in the next one. Okay, so there's the second piece. And here we also want it to be less than or equal to 3. And there's that 0.874 that we came up with. All right. And I did check my numbers when we, to these numbers with those we found in Excel, they are the same. I will go back to our guided notes so we can see those values. Okay, just let it flip here. There we go. So for that equal to 3, we got the 0.197396. These would be good ones for you to test when you're doing examples. So you can go into Excel yourself, go into StatCrunch yourself and see, can I get those? Test your formulas, see if you can get these values. Here's the one where we were strictly less than 2. And here's the value that we got when we were at most 3. Okay, I have one more question before I end this video. And we have a survey found that 20% of all consumers prefer sausage to pepperoni on their pizza. This is not a true statement. I completely made it up just because I wanted something that had a survey involved. And we're going to draw 10 people are chosen at random. And I want to know the following probability. That 8 of these 10 people prefer sausage. And then I do another one down here that more than 3. Okay, so I'm going to draw the, first of all, is this a binomial? Well, let's see. Fixed number of trials. The trials that we have here are the people that we're choosing. So we have 10 trials. Each of these people is our trial. Are they independent? If they are chosen completely at random, they will be independent from one another. Simply because we do know the population is a lot more than 10. So if they are completely at random, the chances of these people being related to each other is going to be very small. So that's the second one. They are independent. Two options. Yes, they're either like prefer sausage or they don't prefer sausage. Those are our two outcomes. Also, the next thing is, does that probability of a success change? And we will use the survey results to be our probabilities. So that's going to remain consistent at that 20%. So for both of these pieces, my N is going to be 10, and my P is going to be that 0.2, that 20%. Here we're looking at the probability that 8, just 8. So we're looking at probability that X is equal to 8. Okay, so we're just going to have to do it that one time. Here we're looking for the probability that more than 3. So more than 3 is more than. So if I'm doing symbols, more than, that'd be a strict this way, more than 3. Okay, this one I can do by hand. This one might be a little bit more work. If I'm doing this one by hand, more than 3 would be 4, 5, 6, 7, all the way up to 10. X is equal to 4 plus X is equal to 5. X is equal to 6. X is equal to 7. Gotta keep going. X is equal to 8. X is equal to 9. X is equal to 10. So from that point up. Now Excel does not do from a point up. They do from a point down, or from 0 to a value. I can get this value by thinking, remember, they all add up to 1. So in Excel, what we're going to have to do is do a 1 minus 0, 1, 2, and 3. And this is where I really kind of like StatCrunch a little bit better. So in Excel, we're going to have to do that 1 minus. And I'll do the hard part first. We'll go into Excel and do these. And then I will come back to StatCrunch and show you why I like StatCrunch for these guys. Okay, so we're going to go into Excel first. Because yes, we can use them in Excel. Will you ever do this in your real world? Probably not, but that is okay. So let's see, the first one we're going to do, again, just equal to 8. So binomial distribution, hit OK. We have 10 trials. Oops, sorry. 8 is our success. 10 trials is down here. My probability is that 0.2, that 20%. For that first piece, we are not doing cumulative. So we get this number, and notice it has this E something. That is a very small number, which means we need to move our decimal point 5 places over. So we're going to have 0.000073728. Okay. This next one I'm going to do from 3 on down. So binomial distribution. Numbers, we're going to go 0, 1, 2, and 3. Number of trials is 10. Probability is 0.2. And here we're going to put in true. So I would be doing 1 minus the 0.879126112. And I can let Excel do that by doing equals 1 minus, and then grab this cell. And there's my 0.120874. Kind of a long way to get there because Excel does not go from a point up. But you can always remember that by adding, everything has to add to 1. So if you're looking for a different group, you can do 1 minus something to get there. Let's go into StatCrunch and see how simple StatCrunch can be for us. Again, I'm going to start over. So again, we're going into Stat, the calculators, binomial. Slide him over here a little bit. Our number of trials this time is, we are doing 10. My P is 0.2. In the first one, we are doing equal to 8. Oops, not 58, 8. Compute. And notice it's not even on our picture here. I can move my picture so we can see it. No, it doesn't even let me. But we have that 0.00007373. Okay, Excel gave me 73728. So same thing. But notice it did not go into scientific notation for us. So it's 0.00007373. So for those of you that are not very good with scientific notation, StatCrunch does a beautiful job for us. For the second part, we were going strictly greater than, so I can show you strictly greater than and 3. And there's my 0.1208. Notice it went 4 on up. We could have done greater than or equal to, changing the 3 to a 4, the same result. I could have done 1 minus this bottom end, which is what Excel has to do. But StatCrunch is very nice that it allows me to choose the inequality that I want. You just have to make sure to be able to interpret those words and turn them into inequalities. Okay, I am going to go back one last time to our guided notes because I put those numbers in there. As soon as it refreshes, there we go. So our probability that X is equal to 8 is 0.00007. I did ask the question here, is this unusual? Which brings up a term that we haven't seen for a little bit. Unusual meant that our probability of something happening is smaller than 0.05. That happened to be our magic cutoff line, that anything smaller than 0.05 is considered unusual. So this would be unusual. Here again, and we walked through it, StatCrunch gave us that 0.12083 just by typing this in. A lot less work than doing it by hand. That would be a lot of grunting, but feel free to practice your formula. You will have access to StatCrunch for tests and quizzes. You will have access to Excel, so do not feel like you have to use the formula. I do give you the formulas for those of you that really want to know them. Okay, I am going to stop sharing now because we are at the end. We have done a lot of examples with the binomial. This one does go a little bit longer, but that is because I did go through the different technologies on how to get some of these pieces. Hopefully I didn't confuse you by flipping back and forth all the time. If you are having problems, please email me so we can get those figured out. If not, we'll see you guys all in the next video. So we will come back to this section again because we're not done with binomial.